Alright, so last time we stopped at the previous slides that we have is in the non-inverting amplifier. I have gave you the video, so I hope you already watched the video. And if you have any question regarding the how to come up with the transfer function for the inverting amplifier, non-inverting amplifier, and differential amplifier, you can just ask me directly. Okay. For the test, I will cover on the first lecture, first slide, which ECG part 1. Okay, for the test one, only up to ECG part 1. The op-amp topics and the following topics will be covered in the examination. Okay. Alright, so we go about the voltage follower or buffer amplifiers. So you might think that why we want to use buffer amplifier? What is the need when we have a gain equals to 1? So we give 5 volts, we get 5 volts, right? So basically the buffer is used to control impedance level in the circuit. So it isolates part of the overall measurement circuit from the output, which that is one of the important things that you want when we want to use the buffer. Okay, usually the voltage buffer has a very high input impedance, and the high input impedance is the, I think, is the important reason that we use buffer or voltage follower. Okay, when we use this buffer amplifier, it will always draw a little amount of current because the nature of the op-amp that have high input impedance. So as a result, the power source will not be affected. Okay, so the output voltage from a source with high output impedance can, via the buffer, supply signal to one or more loads that have a low impedance. So what does it mean? So this is the buffer amplifier. We have high input impedance. Okay, high input impedance over here. So high input impedance, and we have low output impedance, and the gain is equals to 1. The gain is equals to 1. So the AV equals to 1. Okay, so V in equals to V out. So the internal source resistance should be minimal compared to the load impedance in an electronic circuit. So if the source resistance is not minimal, then there will be a voltage drop across the source resistance, and the actual voltage of the source will be small across the load. So let's take a look at the example. A simple circuit consists of voltage source. We have Vs, and that has a source impedance of Rs, driving a load with impedance RL. So this is the RL. Let's say that RL is greater than Rs. So there is a negligible voltage drop across the Rs. So we take a look at the calculation here. Let's say we have our RL is equals to 1000 ohm. Okay, and Rs is equals to 10 ohm. Okay, so when we calculate, so we can see that the voltage drop at the load is 9.9 volt, and the current supplied, V equals to IR, I equals to V over R, which the R is the summation of impedance RL and Rs. So Vs is over Rs plus RL equals to 10 over 1010 equals to 0.0099 M, which is small, and we can say that the current that passing through the load is negligible, as well as the voltage drop across the RS is negligible. It's about 0.1 volt. Okay, and what does it mean? This means that the source is not loaded by the circuit, and the intended source voltage remain across the load. So the current is in the load is negligible. So what we want is actually we want the circuit to deliver 10 volt to the load. Okay, so with this kind of configuration, we can see that only about 0.1 volt voltage drop across the resistance, the internal resistance of the source. So we can deliver 9.9 volt to the load. So it is a good circuit that we have designed. However, the problem comes when the load demands and draw a huge amount of current, because the load is low impedance. Okay. This actually causes huge amount of power to be drawn by the power source, and because of this causes high disturbances and use the power source powering the load. So actually a digital or a buffer serves to transfer a voltage from a circuit that has a high output impedance level to a second circuit with a low impedance level. Okay, so actually when we do measurement from our skin, actually the skin has very high impedance. So when we connect the electrodes to our skin, and then we connect it to the measurement circuit, so what we have is actually we have high impedance level, high impedance level that connected to the measurement circuit. So usually measurement circuit has a lower impedance level as compared to the impedance level of our skin. So there will be a loading effect will occur in the measurement. Okay, so that's why we use buffer. So the buffer, we transfer a voltage from a high input impedance level to a second circuit with low impedance level. So our amplifier has a low impedance level. So if we have a power source and a low impedance load without a buffer, so there will be a huge amount of current drawn from the circuit. So we know that P equals to IV. So when we have a large current, then we have large power drawn by the circuit, which affect the measurement that causes high disturbances to the circuit. Okay, usually a voltage buffer has a very high input impedance, ideally approaching infinity, but in practical it's not infinity, and as a result, no matter what value of the impedance level, the source voltage will always totally span, and the buffer impedance, the voltage across the buffer impedance is the input voltage. Okay, so because the resistance is infinity, the circuit will draw very little current and thus draw little power and does not disturb the original circuit. Okay, we can say that the when the output current generated by the voltage source via buffer, the buffer acts as a barrier between the source and the load, and then preventing the load resistance of affecting the source network. We do some calculation here. Let's say we change the load impedance to 10 ohm in the circuit, and the intended supply voltage to the current will drop to 5 volts. So go back to this calculation here. Let's say our RL become 10 ohm. 10 ohm. This is also 10. So what we have is actually we have 10 over 20. So 10 over 20 equals to 1 over 2 is actually equals to 5 volt. Okay, and then the current will be Vs over RL is 10 plus 10 equals to 20. So 20 is 1 over 2, which is equals to 0.5 amp. So we can see that using the same circuit here, but now the RL equals to 10 ohm and RS also 10 ohm. What we get is actually we get this is 10 volt. We cannot deliver 10 volt to the load. We only able to deliver 5 volt to the load. Plus, the current is 0.5 amp, which is higher than when there is no loading effect. So P equals to IV. It will generate more power, and then it causes disturbances to the measurement circuit. So we don't want this. So that is why we introduce buffer amplifier. Okay. So let's say now we have this kind of circuit, connection with buffer. This is without buffer. So let's say we have 10 volt over here. We know that the current across the what we call input of the amplifier is equals to 0, because ideally there will be no current that will pass through the input of the amplifier, meaning that I equals to 0. So when we have a V equals to IR, I equals to 0, means there will be no voltage drop across this resistor. So the buffer amplifier has one gain. One gain means when we have Vs equals to 10 volt, so there will be 10 volt at the output. Okay, because we have gain equals to 1, plus we have high input impedance at the input of the amplifier, and we have low output impedance at the output of the amplifier. So that's why we have Vs equals to 10 volt. Our output also output of the buffer also 10 volt. So we can have 10 volt source. So when we can have 10 volt that drive the load resistor. Okay. Any questions so far? So what we can say that is loading effect is the effect on the source by the load impedance. So usually loading effect reduces the voltage level of a voltage source. Okay, so just now we have our example. We have 10 volt of our source voltage. So the loading effect will reduce the voltage level of the voltage source. So now when we have loading effect from the previous example, we have 5 volt instead of 10 volts. Okay, so this will cause the attenuation of the signals, and it is not desirable in the measurement circuit, especially if we have if we want to measure small signals that comes from our body, for example. Okay? Any questions so far? Okay, so more questions. We proceed with other op-amp application. Integrators. So the basic integrator is easily defined by the capacitor in the feedback loop. So we have, so in the feedback loop here, we can see a capacitor here. So we know that this is an integrator circuit. So a constant input voltage yield a ramp output. So we give a step input, and what we get the ramp output. So the input resistor and the capacitor form an RC circuit. So the slope of the ramp is determined by the RC time constant. The integrator can be used to change the square wave input into a triangular wave output. Integration is the process of finding area under the curve, and it may represent a single integrated value of the signals. Okay. Usually what we can see in the application of biomedical in a cardiac output machine. So these cardiac output signals is integrated between the 2 points to determine whether its integrated value is in normal range. So we can use the integrator in the cardiac output machine so that we can see from time 1 into time 2 what is the value inside between these two times. So we have a preset value for the normal range, and we can see if the value is fall into the normal range or fall outside of normal range. Okay, that is one example of the integrators. So this is how we do our calculation to get the V out of the integrator circuit. So I'll skip this. I hope you can see and go through this slide. And the other one is we have differentiator. Okay, differentiator. Now what we have is opposite of integrator. So what we have, for example, here we have let's say we have triangular wave. We can get a square wave using the differentiator. Okay. It actually takes a sloping input. It takes a sloping input and provide an output that is proportional to the rate of change of the input. Rate of change of the input. So this is the rate of change. So delta T, so delta V. Okay. So we can what you have learned previously in differential calculus, the derivative process. We can use the derivative process to determine the slope or the positive or negative change of the signals with respect to the time. So using the differentiator, we will know whether the slope is positive or the slope is negative, and we also can determine the peak of the voltage with respect to time. Okay. For example, we can use the differentiators in ECG machine. In ECG machine, we can determine the slope of the QRS complex by this circuit. Okay. Note that the capacitor is in the input circuit. So just now when we have integrator, we have capacitor at the feedback, but for the differentiator, we have capacitor at the input circuit. Okay, any questions? So I leave this slide to you to go through. Any questions? regarding these topics?